Yeah, my name is Oskar, and today we're doing this little journey. I think the screen is a bit off, so I hope the content isn't being cropped away too badly, but we'll see. So we will start here in the valley of programmer death and the vast lands of implicit state, and try to escape over the sea to MTL style, where we will pick up type classes and index monads and stuff. We will cross the kind of value type level boundary, go into Idris land, and eventually we will settle down on these type safe shores out there. This will be a very fast-paced tour of state machines and type systems. I'll show you a lot of examples and a lot of code, and try to highlight what your compiler can help you with. And hopefully I can inspire you to investigate more and learn more about this. I won't have time to explain everything. Okay, state. A stateful program is one that remembers its previous events. We call that the program state, and a stateful program may transition to another state based on its previous state. One problem with stateful programs is implicit state. And with that, I mean that the program does not explicitly define the set of legal states. I hope you can read this. State is instead kind of scattered all over many mutable variables, and it's very hard to follow the program execution and see what's going on, and to kind of verify the integrity of state transitions. And then you start sprinkling runtime checks all over and do defensive programming. So instead, we want to make states explicit. Then it's much more clear how we transition between them, and it makes stateful programming less error-prone. One technique is finite-state machines. And with those, we model a program as an abstract machine, and that machine has a finite set of states. The machine is in one state at a time, and we have events that trigger state transitions. From each state, there's a set of legal transitions expressed as associations from events to other states. Many of you might have heard of finite-state machines before in one or another way. It's a well-known thing, and there are many ways to kind of express them. So for this talk, I'll borrow this definition, which actually comes from Erlang's documentation. So maybe you have seen this before. It says that if we are in state S, an event E occurs, we should perform the actions A and make a transition to state S prime. This is a conceptual model. We won't necessarily write everything as functions with this signature, but we can think of it in this way. Also, we're not talking about mealy or more machines strictly. We won't be doing any explicit hierarchies of state machines. We won't use guards on transitions, with one small example, one exception. And also, we won't go crazy with kind of UML charts and state charts and all that. So I'll spare you those pains. Instead, we will simply model the set of legal states as a data type, where each state has its own value constructor. And you can actually do this in most programming languages, even in object-oriented programming languages. But as Phil said this morning, you should object. So instead, we'll use Haskell, of course. We will encode with algebraic data types instead. And the first kind of real-world example, which I borrowed from a work thing, was this shopping cart checkout. And this is a common example as well. We begin with having no items, and then one or more items can be added to the cart. Then the checkout can start, and all those states in the big box can be canceled from. So there we have kind of a hierarchy going on, but yeah, it's a notational thing. So we select a card, we end up in this card selected, then the card is confirmed, then we place the order, and then we're done. So this is a bit simplified from a real-world example, but it still contains small complexities to make some interesting points. Bit cut off here, but you should see everything. Okay, so here's the state data type representing this same state machine. we have constructors for each valid state. Some of them are empty constructors or nullary constructors, and some carry data. Like HasItems has a non-empty list of cart items, and that gets kind of passed through all the way. And when we have selected a card, we also have a card which is passed through. The events are also a data type here. So the checkout event has one constructor for each event. And some events carry data, like when you select a card item, that card item gets passed. So when we have that in place, we can make our first stab at coding a finite state machine. And we will do this as a function from state to event to the next state. And this doesn't look too bad, right? This is very close to the Erlang thing. But there is one important thing missing. Actions, yes. The problem is that we cannot interleave any side effects here. This is a pure function. So we could kind of simulate what would be going on, but we will still just end up with a terminal state and nothing has happened. Not so useful. So we changed the type to this instead and put an IO on the end. And this means that, so it's a function from state and event to IO of state. And this enables the machine to perform side effects at each transition. We write a new version of checkout that uses this impure IO version. And here are some of the pattern matches of that function. So in case we have no items and you select an item, we construct a list with just one item. And the second case here, then we already have some items, then we just prepend it. Suppose we have this payment provider module, some card thing. We can interleave the side effect of charging a card when the order is placed. All right, so here we use this IO capability. When we run this, we can provide a simple runner looking like this. So this is a function taking such an impure finite state machine, the initial state S, a bunch of events in a list, the E's, and then we end up with the IO of the terminal state. And the definition is just fold M, so it's quite simple. We can easily decorate this thing with logging. So here I have an example which takes some impure FSM and returns another one, but where each transition is logged. When we run this, we will wrap it with logging, and we have the initial state, no items, and then a bunch of events. We will see this output. So we see each transition being logged, and then we have the interleaved effect on the second to last line. So to summarize this part, we have explicit states and explicit events using data types. That's very good. We can provide these standardized runners and logging, metrics, whatever you want, because it's kind of reified into data structures. Instead of having just a list of events, you might think that's a bit naive. You might consider driving this program in another way, like maybe using pipes or whatever library, because usually you don't have the full list of events that are going to happen. There are some troubles with this or concerns. One is that our transitions are coupled with I/O. We're using I/O directly. This makes it a bit harder to test this state machine. We can't do that in pure setting. We could abstract that a bit kind of easy, but I'll show you another technique. Also, a bigger issue, I think, is that while we have the states and the events as data types, we don't have anything expressing the valid transitions between them. So there's nothing stopping us from making an illegal transition at any point. So can we get more flexibility around testing, and can we get more safety? Now we'll go into the style, which I've kind of called, it's known as MTL style, but we've extended it. We will extend it with some other things. So we will use associated types also. And basically, we will start at MTL style, and then we will have some conventions for state machines. Benefits are that we can combine this with regular monad transformers, with the MTL style stuff that's already provided for you, like error handling, logging, and so on. And you can build higher level state machines using kind of lower level ones, compose them together, even though it's a bit fiddly with MTL style because of the classes all have to go together. So we write a type class encoding the legal transitions of the state machine. We represent each event as a method in the type class. Those methods take the current state as an argument and return the next state. We use an associated type alias to make the state type abstract for this type class. This means that the instance of the type class will choose the concrete state type, and we will just talk about some abstract state type. And then we write a program depending on only the type class, and together they form the state machine program at some abstract level. To actually run it, we need an instance. So this needs to be an instance of this transitions type class. It will define which side effects are to be done at each transition, if any. So it chooses the concrete data type, and that concrete data type can contain all kinds of implementation details like database connections or sockets or whatever you need. Okay, but we can also write instances which don't do any side effects. We can have like testing instances which are pure. Okay, so with this technique, we will define our states as empty data types. So here we have a bunch of types with no constructors. So this might seem a little odd, but yeah, we can't construct values inhabiting these types. They are only used as marker types. You'll see how very soon. Then we define this checkout type class, which will contain all the events and the transitions. The associated type state of M has kind star to star. And how many of you here are familiar with kinds in Haskell? Okay, almost half. That's good. So a kind signature like this is basically, you can think of it as a function from one type to another. So star to star basically means type to type. So it's a kind of a function at the type level. So this state will take a type and return a type. And that type that we pass in are those empty types we saw before. So we parameterize it by some marker. Now let's look at these methods. The initial method is simple. It just gives the starting state. So we don't pass any state into it. We just get the starting state. It's parameterized. The associated state type here is parameterized by the type for a specific state. In this case, it's no items. Some events are very simple. So they transition from one state to another. So confirm in this case transitions from card selected to card confirmed, right? Some are more complicated. So if you remember from the diagram, we had both no items and has item states accepting the select event. You could select one more item at the start or when you already had some items. So it's the same event being kind of overloaded. So we have to be able to pass one of those states, either the has items or no item states, into the cancel event. So we could use an either for this, but I think it's a bit more clear what's going on if we have a specialized data type for it. This communicates what's going on better. So we define select state, and this has one constructor for each valid state where you can select one more item. So we kind of wrap two different types in a sum type like this. Then we pass a select state instead to select. And a cart item, the next item you want to select. And we get back has item state. So we have two kind of source states in the event and one state on the outside, on the return. In the same way, basically, but there are, for cancel, there are 3 states accepting cancel. You saw the big box and you can cancel kind of all the way through. So there we couldn't use either. It would be even more confusing. So we create the data type again, cancel state, which has 3 constructors. Same thing going on. In cancel, we pass a cancel state to it. Here is the complete type class. It's a bunch, I know. But this, if you squint a bit, you can see that this corresponds very nicely to the diagram we had before. This contains the same information in a way. So let's write the program using our type class instead. FillCart constrains M to be a monad with checkout and I/O operations. So now I should point out here that I'm using I/O directly in this part of the program just to drive it, to get user input and to make some progress. You could abstract that away if you like to make it more testable. I haven't done this here just to keep the complexity down a bit. Anyway, so this type says that it transitions from no items to has items. It asks for an item and selects that. And then we have to wrap it in this select state constructor. Finally, fillCart hands over to select more items, which we'll see now. This type says that it remains in the has item state, so it loops there. If the user wants one more item, it selects that and recurses. Otherwise, it just returns the state it had. Start checkout has a type saying it goes from has items all the way to order placed, so the end of the whole thing. That matches very nicely what we have so far. We ask for a card and a confirmation. And as soon as we transition state here, you see that we need to start using the resulting state value instead. So we have a state value, pass it into an event, it transitions, we get back a new state value, and then we have to start using that. So each time we transition, we need to start using the new state value. We can't really cheat and skip a step. So that's good. In the end, if the user confirmed, we place this order. If not, then we cancel, go back to selecting more items, and restart the checkout. So it will just loop until we reach order placed. This is the main program, creating the checkout flow, running it, and then eventually ending it. We get back an order ID when we're completed. So far, we have only seen this abstract part of the program, depending on the type class. To run it, the part we have seen so far forms this abstract program that can be run in different ways. To actually run it, we need an instance of checkout. And this instance will decide both the concrete state type, which is used to pass around, and also if there are any side effects going on and so on. We will use this instance to run the checkout program, the abstract program. This is the concrete state data type that we will use. And this is a bit daunting, but OK. This is a GADT, which is an extension in Haskell. So basically, it's a data type, but we provide the type signatures for each constructor ourselves. It has one constructor for each state. And each constructor maps to one of those empty state data types from before, those with no constructors at all. So here we kind of tie together this concrete state type with those abstract type tagging types. No items here. If you're familiar with Haskell, you might notice that the no items constructor here is not the same thing at all as no items, the type. No items here is a constructor in the GADT, and no items the type is that empty type from before. So you could say that this checkout state type is a concretion of the abstract state type. OK. Given that we have a bit of machinery to run this MTL-style checkout T type, this is the regular kind of boilerplate you do with MTL, unfortunately. We can then define this instance. So we say the checkout instance for checkout T. And then we associate our concrete checkout data type for checkout state with the kind of abstract state type. So for this instance, state will be checkout state, basically. Let's look at some of the instance methods. The initial method simply constructs a no item state, no side effects going on. Select will prepend an item to a new or existing list, basically like before, returning has items. But you can note here that we work with our concrete state data type in these methods. And we don't have to handle any state event mismatches because we have the type system checking each transition, and the compiler actually knows that this is exhaustive. So each state we pattern match on will be just a valid state that could go in there. Same thing goes on here. We're in place order. You see card confirm is the only thing that can go in here. So we don't have to throw errors on incorrect transitions. This generates an order ID, calculates some price, charges the customer. So here we have a bunch of side effects going on. And finally, returns this order place state. We can run this abstract checkout program using run checkout T, and we end up in I/O. We could, again, write the instances for tests, which didn't use I/O. Sorry. OK, to summarize this technique, we've modeled state machines using type classes and MTL style. We've used associated types to abstract the concrete state data type for each implementation. And we use these explicit state values being passed in and being returned from each transition. Also, we have this abstract program, which only cares about the type class, and then we run it with some instance. OK, this is a bit stricter than the ADT-based version we had in the start, because we also encode the state transitions in code and in types. But it's not necessarily safe, because these state values that we pass around, those can be reused or discarded. They can be consumed 0 times, 1 time, or more than 1 time. This makes it possible to re-perform side effects illegally or by accident. And there is nothing really enforcing us to go to the terminal state to have the program eventually do to cancel and exit properly or perform the whole checkout flow. So as an example of reusing state values or consuming them multiple times, we place the order, and then we do it again. We kind of mock the user, and and then we end. So they have been charged twice. I think there was some Bitcoin exchange doing kind of this the other week. I don't know. But this is not our business model, right? So the compiler should say, like, UX broken, like, do it right. OK, so one solution to this problem would be to grasp for linear types, right? We then know that each value is consumed exactly once, and we wouldn't have this problem. But another problem is that GHC or Haskell doesn't have any linear types, at least yet. So I won't be using that. Instead, we will use a solution where we bake the state, instead of passing around states explicitly, we will bake it inside the monad. And then we can do this instead. So if we place the order twice, we get a type error the second time. We're not in that state. We can't do that operation. To accomplish this, we have to parameterize the monad by, or index it, as it's called, by the state types. Otherwise, we couldn't get any type error here. And that brings us to index monads. Index monads, have anyone heard of this concept before? A couple. Cool. Then you'll learn all kinds of new stuff, or at least have heard of it. So an index monad is, as the name kind of suggests, a monad that is indexed. What is it indexed by? Well, 2 new type parameters, input and output. you can see these as the type before and after this computation. So if we look at the IX monad type class, this is basically from the index monad library in Haskell. I think it's just called index. I can't remember. Anyway, this is the kind of head. We see that the index monad M has the kind K to star to star. That sounds very scary, right? But the K is any kind, and it's the same kind for the input and the output. And then the star is the monadic return value as regular monad. So a regular monad would just have the star to star here, but now we have two Ks as well for the input and the output. Okay, and there is one interesting operation here called iBind, which is analogous to bind in monad. So I will do a comparison. How many of you know how bind works with monad? Yeah, that's good. So this is the signature for bind, basically, where M is some monad. And yeah, this is not a monad tutorial. This is an index monad tutorial. So let's go. Okay, we have a bunch of new things going on here. I, J, and K all over. So what's going on? This looks a bit messy, right? A lot of letters everywhere. The input of the first monadic computation, that's the left one. The input type is the input of the resulting monadic computation. That's the red arrow going all the way over, and the I's being matched. The output of the second monadic computation, the one that's kind of bound, that's the output type of the resulting monadic computation. That's the blue arrow there, K to K. And then the J is the intermediate index, and that's the green arrow. Okay, so if you squint a bit, this might remind you of function composition, right? You have two functions, and the type in between goes away. You get a bigger function. Same kind of thing going on here, but with the indices instead. If we format it a bit differently and specialize this iBind to our state types, maybe, it could look like this. So if you iBind one computation from state 1 to state 2 with a computation from state 2 to state 3, we get one big computation from 1 to 3 directly. As a last concrete example, we will use these two operations from the checkout flow. So we bind them together, and the result transitions all the way from has items to card selected. Okay? Okay. We'll take questions afterwards, I think, but so keep them in memory if you can. Okay, so using this index state monad, we hide the state inside the monad. Only the type of the state is visible. And we cannot use a computation twice unless the type permits it. Okay? The indexed monad can describe one state machine at a time, like one resource or one state. This makes it hard to compose because we want to have multiple state machines in a single computation, possibly, like opening two files being two state machines and copying stuff from one to another, or a ticket vending machine or whatever, having a printer and a card reader, so on. So one solution here is to have a type as the index which maps a name to a state, or maps multiple names to multiple states. So we can represent many state machines going on at the same time. And then those are independent, and we apply events by name. So now let's look at some pure script, just for fun. Pure script, because really this is much harder to do in Haskell, so we will use pure script for this example. In pure script, they have a row kind, which is like a type level record. So here we have a row saying out is a file and in is a socket. So out and in are the names or fields. Labels, I think it's called. These can also be polymorphic. So we can say for all R, like a row type variable, we will have a row that has at least out, file, and in socket, and possibly other fields. And these are used regularly in pure script to do records and effect types. So here we construct a record with those two fields, which this is just syntactic sugar for the same thing. Okay, these can be used in our state machines. So here's a small example where the initial event goes from a row R and adds the my machine in its initial state to that R. The second example transitions from state 1 to state 2 only for the my machine, and the other resources or things in R remain the same. So you can combine these. And this last one goes from a row with my machine to a row without it, so it deletes it. And then we can have a type signature requiring that each created state machine must be removed. So in this example, we go from an empty row to an empty row. So everything that happens in this computation has to kind of clean up after itself. Okay, there are some examples here. I'm shamelessly plugging 2 libraries of my own, the 2 last ones. But the first thing is a cool library in Idris, which if I have some time, I will show it to you now. These are for PureScript and Haskell. So you can do some stuff in Haskell as well. If you're interested in index monads, check out this blog post and introduction on Quang's Haskell blog. Very good. There's a package in Haskell called indexed. You can use this extension, rebindable syntax, to use do notation with index monads and get crazy. And yeah, you can do weird stuff with session types together with this. So lots of cool things. Very quickly, I'll just throw some Idris at you, and we'll see what happens. Idris is nice. Very cool language, which we can grab some ideas from. Maybe not use in production. Actually, the website says like it's not for crucial things. But I like to steal some ideas from this language. So it makes it nicer because we have dependent types, and we can use that for things like error handling and having dependent state types, which is really nice. And the thing where we had multiple states accepting the same event, we can express that cleanly. Yeah, check out this tutorial, this one. Okay, so this is what we had before, but in Idris, if you look at those the 2 first states, no items and has items, they kind of say either 0 items or more, right? And that's very close to a natural number and the natural number encoding you usually see in Idris. So what we can do is to use the natural number and collapse those 2 into one thing being parameterized by the number of items we have. And then the select operation increments that number, and there's a guard. When we do checkout, we have to have at least 1 item. Otherwise, it's the same. Okay, in Idris, we have these kind of type aliases for things. So this is just some prerequisites. The items of n is really a vector of n items. Okay. Other things are strings. Our state is a sum type here as well. We pass this natural number, the nat, through all the states to keep track of how many items we have. The checkout interface has this state type. This is very similar to the associated type thing we had before. So here we say which is the concrete state type. Okay, here's an operation. This adds a state of has items of 0, right? And we get this var back. You see var. So we don't have to name our state machines, come up with cool names like my machine. We just get this var back, which is like an opaque identifier we can pass around. So when we do the select operation, we pass in that identifier, the var, and the item, and we go from having items, n items, to having the successor of n items, plus 1. When we do a checkout, we require it to be not 0. So the successor of some number is not 0, right? And then we go into the no card state with the same number of items. Again, we have this thing where we have 3 states accepting the cancel event, and we want to encode that. So we can use a predicate over state types in Idris, and basically say to the caller of this operation, you have to give me a proof that your current state accepts cancel. The proof is a value of this type. Yeah, I won't go into much detail here, but basically in the signature you tell Idris, can you automatically create a proof that my current state S, that's S, is a cancel state, that you can create a value for it with n items. And then we continue with n items. Okay? Then we write the program using these operations. So select more will just select one more item and ask a question nicely. Check out with item transitions from has items to order place all the way to the end. Okay? Or it stays in has items if the checkout is canceled. So here you see the dependent types going on where the return type decides the return value decides the return type. We ask for a credit card, and eventually we will place the order. And you see all these continual cancel be sprinkled through. Those could only occur on those places because of the types. That's kind of cool. Checkout or shop removes a resource from the in-state has items. Okay? And it will try to check out with items and complete the checkout flow. But if the user cancels, it loops back to go shopping, which we will see now. I know this is a bit confusing and fast, but let's go. Go shopping will select one more item. Then we ask if the user wants to check out. If not, then we just go shopping. And these two last functions that you've seen, those two, will go back and forth until the user has reached the end and bought their stuff, right? So we start this program by creating the initial state machine and go shopping, okay? And if you have seen this total keyword, we tell Idris to make sure that all those functions are total, right? So if you have a hard time at work convincing your boss, like, I want to use Idris, you can tell them that you can prove that your users will buy your stuff. Very good. To have these total functions that loop, we need to use run loop. And there is one little trick here. This value called forever, that's partial. That's like recursive value, which fuels this computation, so to speak. And if we run out of foreverness, we print oops. Yeah, that's the Idris one. So to summarize this, implicit state is hard and unsafe when it grows. We can have a better kind of documentation and understanding of our program by making it explicit and not have to do defensive programming. You probably have these hidden state machines in your code, which you might benefit from formalizing in a way. You can use data types for states and events and possibly transitions like I've shown you. And you can gain a lot by just doing that in most programming languages. We can lift more information to the type level and get some more safety around transitions and stuff. So like Haskell and PureScript are good examples, but you can also steal some ideas from Idris and similar languages or linear types or whatever. But I urge you to start simple. Use data types and take that step first and see where it gets you. Because that's like the 80% of the journey. But it's fun to experiment, right? So key takeaway is to redefine this design in your code. Yeah, and with that, I'll take some questions.
Thank you for a nice presentation. Okay, the questions, maybe you can use the mic.
Hi, thank you for the great presentation. I would have one question. If you have more complex use cases, won't there be a problem that the restriction rules for the state machine in Haskell go out of hand, so they grow quickly? And how can you deal with such a problem? Do you then split the one use case to smaller ones and then they interact like separate state machines, or how do you deal with such a situation? Thanks.
Yeah, good question. So I guess the happy path is kind of nice. And I only showed you basically the happy path in the Haskell version, right? So error handling can become a problem. I guess that's tricky. That's where it explodes. And if you look at the Idris examples more closely, you can see error handling being like a first-class thing in that framework, so to speak. So it's much easier in Idris to do the error handling. In Haskell, you'd have to do a lot of explicit stuff, and as you say, it might blow up. But if you can split it and somehow, isolate the error handling within a smaller area, then it might work. But also worth noting here is, I think you shouldn't okay, let's rewrite our whole system with this technique. You can use it as like a local thing. And I've experimented with using this for a part of a web app, for instance. And there is a framework in Haskell called mflow for doing basically these, what's it called, like workflow web wizards, basically. And then you can use this kind of technique in isolated area. So, yeah, I hope this answers your question. Yeah.
Okay, other questions? Yeah.
Thanks for the presentation. And do you happen to know the alternative approach to modeling state machines based on phantom types and how it relates to the ones you've presented?
Modeling with phantom types?
Phantom types, yes.
I'm not exactly sure what you're going for. But
okay, I'll be glad to explain you.
Yeah, we can talk.
Thanks.
Yeah. Okay, thanks.
Okay, one more question over there. Yeah, please.
What
go
was
ahead.
your specific use case? If you can talk about it. Or was it just your research for your interest?
Yeah, so the question was, what was my use case at work? So I didn't use the Haskell implementation at work. I just took the example from work, but we had a big complicated checkout flow where a lot of stuff going on in the session. So we had, and that was in Clojure. So, and requirements change. Can you please put in a step between step 4 or 5? And also do coupons or do like a optional login wherever. And it just explodes in complexity, and we had no idea what was in the state type or the session type. And so that kind of led me into looking at this. Would it be reasonable to make this like a explicit state machine for a business kind of flow? But I didn't use this technique at work. No.
Okay, there's one question on the back.
Yeah.
Functional programming, mostly for safety.
Yeah.
But my question is that what are your experiences on this method as the size of the state machine starts to grow, and as such the number of invalid transitions start to grow, which you have to handle, as you said, error handling and logging explodes at that in that case. And I am specifically thinking of if one would want to re-implement OpenGL in a higher language, and the OpenGL state machine is fairly large with a lot of bad transitions.
Yeah, so right here. Yeah.
And would you consider doing something or that is just too big?
Yeah, that's interesting, because I think when this was the hotness around UML, as I've understood it, people were trying to use these hierarchical state machines. So if you could like compose state machines, and you get error handling locally, and you get error handling composed in some way, and that tried to tackle this complexity of a large system expressed as one big composed state machine. I'm not sure if anyone succeeded doing anything useful with that, but in this approach I've taken here, it's quite simple, so I don't have that hierarchical thing. So trying to tackle something like OpenGL would probably need to be more, you would need something more powerful to go there. So yeah, I wouldn't do that, I guess. But in a way, if you look at it like this, basically what this does is highlight the problem more. by making these things explicit. You said you have a lot of invalid transitions everywhere, just start throwing errors. You would do that anyway, but you wouldn't know about it, kind of. Yeah. So it's not that you can't do it with this technique. You will see how much it hurts, basically. I think. Yeah.
Yeah. Okay. Thank you for nice discussion. And
one more question.
yeah,
if we have
maybe.
time.
Yeah, we can have one more.
Yeah.
So speaking of the hotness with UML, you said that one of the slides, if you squint a little bit,
Yeah.
you can see the relationship between the picture and the text.
Yeah.
Is there kind of automated tools to generate the pictures from the text?
Yeah.
Vice versa,
I listed this motor library for Haskell, which uses this convention. And if you use that, it's extremely experimental. I put some hours on it, but you can generate like a graph vis thing from the type class. Yeah. So you can do stuff like that. Yeah. Okay.
Yeah, so I think, thank you for this discussion. It was a nice session, and I think we're just in time. The lunch should be upstairs, as far as I know. We are going to meet again in 1 hour, so if there are any speakers for the next session, you can try the projector and so on. And yeah, let's thanks Oskar again. Thank you.